Okay, welcome back. MAT 1350. This is Wednesday, July 28th. I'm very sorry, but I got booted out of my own class because of my internet connection issues. So, picking up where we left off, what we were doing was talking about angles that we can make on a circle. We're not yet at the unit circle, but any angle that we make on a circle, essentially what we do is we take the coordinate points of that point, where it lies on the circle, we make a reference triangle, as we see here in problem 3, and we can calculate the sine, cosine, and tangent after we find the value of the hypotenuse, which is the same as the radius of the circle. Now, in problems 1 and 2, when we are writing down the trig ratios for sine, cosine, and tangent, well, it's kind of nice because we're in quadrant 1 and all the ratios are positive because our coordinate points are also positive. But as we look at problem 3, well, when we calculated the hypotenuse, we can use a positive 5 and a positive 12 because we're just calculating a length of a line. However, since the coordinates are negative 5 and negative 12, those negative numbers are part of the sine, cosine, and tangent ratios. So let's finish up problem number 4, where we have an x value of positive 3 and a y value of negative 4. All right, and let's find our sine, cosine, and tangent ratios. Oopsies. All right, so we've got sine of theta. And we're going to use this little reference triangle that we made by connecting our coordinate point with the x-axis. All right, so our sine of theta, even though theta is this big old angle that's clearly bigger than 180, clearly bigger than 270, we're still going to use just this little triangle to determine the sine, cosine, and tangent of our angle theta. So the sine is opposite negative 4 over hypotenuse, so negative 4 over 5. That is fully simplified. The cosine of theta is adjacent over hypotenuse, that's 3 over 5. And our tangent, well, that is opposite over adjacent, negative 4 over positive 3, so that's negative 4/3. All right, so what we've just discovered is that sine, cosine, and tangent could be positive or negative. So that brings us to the unit circle. Now, the unit circle looks just like those other circles that we saw. The only difference is it's called a unit circle because our radius is always equal to 1. Why is our radius equal to 1? Because this just simplifies all our ratios for us. All right? Now, the gist of this unit circle is basically that what we can do in order to simplify all of our trig ratios is simply use the coordinates x and y to identify the sine and cosine of any angle formed on the unit circle. Why? Because our hypotenuse is 1. We said our radius of our circle is 1. That means the hypotenuse of any triangle. What if I drew this coordinate point, whoops, and a triangle here, right, a reference triangle. Okay, so if I draw my reference triangle here, take a look. This coordinate point here doesn't matter because our radius equals 1. All right, so if we were to calculate for theta, which would actually be this angle right here, theta, well, what is our, this leg down here, our adjacent leg, is going to be the x-coordinate, and our opposite leg is going to be the y-coordinate. So the unit circle basically tells us that as we move this blue dot around the circle, since the radius is 1, when we calculate the sine of theta, well, opposite over hypotenuse. The sine of theta is going to be y over hypotenuse 1, which is y. The cosine of theta is going to be adjacent over hypotenuse, x over 1, which is x. Guess what? If we do that over here in quadrant 2, we say the sine of this theta, let me just make this a different color. Sine of this theta is going to equal, again, the sine opposite over, oops, sorry, that theta. Yep, opposite over hypotenuse, y over 1, which is y. The cosine of this angle theta is going to be x over 1, which is x. And I think you get the pattern if we put this, make a triangle in quadrant 3 by just putting a coordinate, a point on the circle here, for example. Boop. We're going to have the same exact pattern. Sorry, that x, I didn't mean to put that x in the box. Let me just fix that up. And so here in our notes, what we can do to simplify is say that the sine of any angle theta on the unit circle where our radius is equal to 1, the sine of theta is always going to be our y value, the y coordinate. The cosine of theta is always our x coordinate. That is it. That is the gist of it. Let me just fill in these values here. Let me do one last one. Say we have this point right here. Alright, this is going to be y. This again, our radius is 1, and this will be x. So, let's talk about then the sines, SIGN, of any angle theta on the unit circle. So, here, in quadrant 1, well, if the sine of theta is our y coordinate and the cosine of theta is our x coordinate, look at this, both x and y, sine of theta and the cosine of theta are positive. Greater than 0 means positive. Okay? To the left here in quadrant 2, let me just change up the colors here. In quadrant 2, well, our x coordinates are negative, so the cosine of theta is less than 0. Our y coordinates, in other words, the sine of theta, are positive, so greater than 0. So any angle that lands in quadrant 2 is going to have a positive sine value and a negative cosine value. Ah, okay, interesting. This is one way of checking our work. I hope you're recognizing. Now here, in quadrant 3, well, look at where we are. We're on the negative x and the negative y axis. So any point here on the unit circle, any angle made by connecting terminal ray to any of these points here in the unit circle, well, our y coordinates, so our sine of theta, are negative, and our x coordinates, cosine of theta, are also going to be negative. Lastly, when we swing around to quadrant 4, we notice our x values are positive, so our cosine of theta is going to be positive, but our y values are negative, so the sine of theta will be less than 0, cosine of theta will be greater than 0. So, let's just do a little bit of a quick check for understanding. Okay, I messed up the recording a little bit. What I wanted you to do was pause the video and answer questions A, B, and C. So please pause it. I know you've already got the answers for A and B, but try question C on your own, then press play again to get the answer. Alrighty, so we've got our answers for questions A, B, and C. Those are just quick checks for understanding on just the sine, positive and negative sine values for the sine and cosine values on the unit circle. So now let's talk about some specific angles on the unit circle. There we go. Now, this circle you should recognize from Monday's class, Monday, July 26th. We have the degree, the angles written in degrees and written in radians. We have, remember what we said when we were working on identifying the trig values for any point for any angle made with a circle. We've got we can use reference angles. So let's take a look at what the angles are with the reference angle of 30 degrees. There are 4 of them. You can see them. They're color coded. They are these ones. Oopsies, I'm sorry. if I drop an altitude right here, oh no, I'm sorry, that's not the reference angle of 30. Oh yeah, that is 30. Yeah, because this is 30 degrees. If I drop this altitude right there, I've got a reference angle of 30 degrees, and if I've got this angle right here, 330 degrees, my reference angle is 30 degrees. I'm sorry, same here. So these four angles have a reference angle of 30 degrees. So I'm just going to write them in degrees. Notice they're all also multiples of 30. 30, 150, 210, and 330 degrees. 30 being pi over 6. Notice in radian form, they're also over 6. Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Now, angles with a reference angle of 45 degrees, and believe me, we're going somewhere with this. We're coming back to the special right triangles that we talked about earlier, are obviously 45 degrees. This one right here. All right, so we've got 45 degrees right here. 135 degrees, because our reference angle here is 45. 225 degrees, because this reference angle right here is 45 degrees. And 315 degrees, because this reference angle right here is 45 degrees. So let's just jot these down. They're all, you'll notice, multiples of 45 degrees as well. 45, 135, 225, and 315. You will also notice that each of these angles has a radian measure over 4. So it's pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Notice we're increasing by 2 in the numerator. So many beautiful patterns. Alright, lastly, let's just jot down our angles with a reference angle of 60 degrees, and those are the green ones here. And after this, I'm going to stop this video and start a new one to explain all of the values on the unit circle. Alright, so this angle right here is 60 degrees. Alright, another angle with a reference angle of 60 is this one right here. Why? Because this is a 60-degree angle right here, so 120 degrees. Alright, 240 degrees also, if we make this triangle. Our reference angle right here is 60 degrees. And I hope you're recognizing where that 60 degrees comes from. Alright, so this is 240. And this angle right here, 300 degrees, if we make our reference triangle, we have another 60-degree reference angle. Oops, this. So 300 degrees. Oops. You'll notice these are all multiples of pi over 3. Pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Why not 3 pi over 3? Because guess what? 3 pi over 3 is simply 1 pi. Okay, I'm going to stop this video right here, pick up at the next one.